We've looked at what happens when light meets a reflective surface. It reflects off of it. This video is going to be about a different thing that happens, and this is called refraction. If I have a surface like this, an interface, and I have a light ray that's incident on here, like this, incident ray. I know that what I need to do is draw a normal vector. And I know that I'm going to have a reflected ray that looks like this. I also know right here that this incident angle is important, and I know that my reflected angle is the same. But not all light that hits an interface has to bounce off it. An interface also is just the name for when one medium and another come together, and a medium is whatever light is traveling through. So I want to do this. What if this light ray didn't bounce off, didn't anything? Then it would just continue like this. So this would be the projected path. When this light ray hits this new medium, this is called medium 1 up here, and we'll call this one medium 2. When this hits a new medium, what's going to happen is that light ray is going to change its path, and we can figure out just how it's going to do that using something called refraction. I'm going to approach refraction by means of a shopping cart. So I will come back to this in a moment. So I have a shopping cart. If I'm driving this thing along this way, I'm moving at one constant speed. But then I hit some kind of an object on the ground, which is usually some kind of a berry or something, and things happen. So let me look at this from above. So I've got my same shopping cart from up above, and I've got my wheels right here. 1, 2, 3. I'm going to leave the bottom of the shopping cart just blank because I think it's going to make it a little easier. And I'm moving along this way. When I encounter that one random berry that's stuck on the ground like this, what happens? My shopping cart turns. I start going now this way. And I do that because this front wheel has slowed down. And because it slows down, I move in that general direction. I move toward, I turn in the direction of what's slower. So now I want to relate this back to refraction. I was moving this way, and maybe medium 1 is a fast medium. Light moves quickly through here, and medium 2 is a slower medium. So I am hitting a berry, a whatever, cherry or something, and I'm going to pretend that I am hitting that I've got my shopping cart this way. 1, 2, 3, 4. And that I'm going to be tripping this wheel. When I trip this wheel, my shopping cart is going to turn that way. So now what this means is that I'm going to have a refracted ray that's going to turn this way, away from the projected path toward the normal. So I get a bending of the trajectory toward the normal. I'm going to call this my refracted ray. And I will call this my angle of refraction. Refraction and reflection both begin with an R. They actually both begin with REF, which makes subscripts difficult. There is a different word for this, kind of. Refraction is the bending of this light path. Transmission is the movement of light from one medium into another. So I'm going to actually call this an angle of transmission or angle of refraction. And I would like to come up with some kind of an equation that relates these. To do that, I need some values. Now I've got here fast and slower, but surely there is some way of quantifying this. And there is something called an index of refraction. And an index of refraction, which gets a letter N, is defined by the speed of light in a vacuum divided by the speed of light in a medium. So let me get there. This is a unitless quantity because I am dividing a speed by a speed. C is the constant that we use for the speed of light in a vacuum. Or in empty space, if you like. And that is 3 times 10 to the 8th meters per second. V, this is the speed of light in the given medium. If I'm looking at air, the speed of light in air is almost exactly the speed of light in a vacuum. It's just a tiny bit slower. So the index of refraction is always going to be at least 1, right? And is going to be greater than or equal to 1. If I'm moving through a vacuum, I get an index of refraction of 1 because I will get C over C. If I'm moving in anything with more material in it than a vacuum, which is really anything at all, if I'm moving in air, I will move a little bit slower. So my V will be a little bit less than C. I will have C divided by something that's a little lower. I'm going to get an index of refraction that's a little bit bigger than 1. For air, it's a 1 point, and then it's followed by a couple of zeros before other things start happening. So we just treat that as 1. If I'm moving through something like water, then I'm going to get something like a 1.3, 1.35 type of number. For glass, I'm going to get like a 1.5 type of number, but that gives me a reference point. So now I've got this index of refraction, and I need to come up with an equation. And I get that. That equation is called Snell's law. And it states n incident times the sine of the incident angle equals n transmission times the sine of the transmitted angle. Or sometimes you'll just see it n1 sine theta 1 equals n2 sine theta 2. Now it really matters that we're measuring off of the normal, because if we measure off of the horizontal, off the interface, then we come up with an equation that doesn't work, or it doesn't obey this equation anyway. So this gives us an equation that lets us make a couple of good calculations. If my n2 is smaller than my n1, then my sine theta 2 is going to have to be bigger than my sine theta 1, right? If this number is smaller, this number is going to have to be bigger if we're going to keep it equal over here. And the sine of an angle increases like the angle. It's not exactly a similarity thing. For small angles, it's pretty close, but maybe I should say it this way. The sine of an angle increases when the angle increases. That's what I've got. That is Snell's law and reflection.